So the last class we are discussing about the design techniques for linear phase FIR filters. Design techniques for linear phase FIR filters. Okay. So here we have three methods of design techniques for linear phase filters. So those are Fourier series method, Windows method, and frequency sampling method. Already in the last class we discussed about the Fourier series method, right? Fourier series method. So this is the Fourier series method. So this was already discussed in our last class. So second method is Windows method. What is that? That is Windows method. Okay, Fourier series method and Windows method. So this is all Fourier series method. Here these are the three important methods are the Fourier series method, Windows method, and third one is frequency sampling method. So let us see the Fourier series method once. So the result frequency response of an FIR filter can be represented by the Fourier series HD of e power j omega is equal to sigma n equal to minus infinity to infinity HD of n into e power minus j omega n. This is nothing but Fourier series of HD of n, right? This is equation number 1, right? Where the Fourier series coefficients HD of n are the desired impulse response sequence of the system. The samples of HD of n can be determined by using the equations, which is nothing but inverse Fourier transform, that is HD of e power j omega, right? HD of n, how to get HD of n or x of t 1 by 2 pi into integral minus by 2 pi HD of e power j omega t e power plus j omega n d omega, that is equation number 2. So the impulse response HD of n from equation number 2 is an infinite duration sequence. This is HD of n from this is having infinite duration sequence. For FIR filters, we know that there infinite impulse response to a limit duration sequence of length n, where n is odd. So h of n equal to hd of n for n equal to minus n minus 1 by 2 to plus n minus 1 by 2, it is 0 otherwise. So taking Z transform of h of hd of n or h of n, we get the Z transform of h of n is nothing but h of z, that is equal to sigma n equal to minus n minus 1 by 2 by plus n minus 1 by 2 into h of n into z power minus n, right? So it is equal to sigma n equal to minus of n minus 1 by 2 minus 1 h of n into z power minus n plus h of 0 plus sigma n equal to n minus 1 by 2 h of n into z power minus n, right? So we can write this as n equal to 1 to n minus 1 by 2 h of minus n into z power n plus h of 0 plus sigma n equal to 1 to n minus 1 by 2 to h of n into e power z power minus n, that is equation number 4. So impulse response in symmetry, that is h of minus n is equal to h of n, right? So h of z will become h of 0. So h of n will become h of 0 plus h of n, instead of h of minus n, it is symmetric. So it will become h of n. So that h of n will be taken as common, h of n into z power n plus z power minus n. Let it be considered as equation number 5. So this transfer function of the Fourier filter h of z represents a non-causal filter. So due to the presence of positive power subject, so this is a non-causal filter. So the transfer function h of z is not physically realizable. So realizability can be brought by multiplying equations 5 by the samples, where n minus 1 by 2 is the delay in samples. Hence, we can see that causality is brought about by multiplying the transfer function by the delay factor alpha, delay factor. So multiplying the equation number 5 by delay factor, so that the causality condition will exist. Okay. Okay. So multiplying the equation number 5 by the delay factor alpha equal to n minus 1 by 2. This modification doesn't affect the amplitude response of the uh, filter. So however, the abrupt transformation of the Fourier transform results in oscillations in pass and stop band. These oscillations are due to the slow convergence of the particularly near the point of discontinuity. Okay. Okay. These effects is known as Gibbs phenomena. Those effect is known as Gibbs phenomena. Okay. The considerable oscillations can be reduced by the multiplying the desired frequency response coefficient by the appropriate window function. Okay. So this is called Gibbs phenomena. So design procedure for digital FIR filter by Fourier series method. Okay. So the specification of digital filters are the desired frequency response theory of j omega, the cutoff frequency omega c for low pass and high pass filter, and those are WC1 and WC2 for band pass and band stop filters. No, we have to note that if analog filter cutoff frequency FC and sampling frequency FS are specified, then calculate the cutoff frequency of digital filter omega c using the equation omega c equal to 2 pi by Fs. The number of samples of impulse response n. Determine the desired impulse response Hd of n by Hd of n equal 1 by 2 pi, taking inverse Fourier transform of the desired frequency response Hd of e power j omega. Okay, this is the problem, like problem. Okay, it is can be solved like this. So Hd of n equal to, what is the formula for Hd of n? That is inverse Fourier transform 1 by 2 pi integral minus pi to pi Hd of e power j omega to d omega. So calculate n samples of Hd of n for n equal to minus n minus 1 by 2 to plus n minus 1 by 2. And from the impulse response h of n equal to Hd of n is minus n by n minus 1 by 2 to plus n minus 1 by 2 with n equal to 0 and so on. Okay. So we have to note that the impulse response is symmetric, therefore h of minus n is equal to h of n. Hence it is sufficient we calculate h of n for n equal to 0 to n minus 1 by 2. Okay. Take the Fourier transform of impulse response to get the non-causal transfer function of filter FIR filter h of z is equal to sigma n is minus n minus 1 by 2 to plus n minus 1 by 2 h of n into z power minus n. Okay, it is equal to h of 0 plus already we derived earlier sigma. This is h of 0 plus sigma n equal to 1 to m minus 1 by 2 h of n into z power minus n plus z power n. So convert the non-causal transfer function h of z to causal transfer function h dash of minus z by multiplying h of z by z power minus of n minus 1 by 2. So h dash of z is equal to z power minus of n minus 1 by 2 into h of 0 plus sigma n equal to 1 to n minus 1 by 2 h of n into z power n plus z power minus n. So derive suitable structure for realization of FIR filter. Okay. So that is about the design. So design and now next problem. Design an ideal low pass filter with frequency response Hd of e power j omega is equal to 1 for minus pi by 2 is less than or equal to omega is less than or equal to pi by 2 and is 0 for pi by 2 is less than or equal to omega is less than or equal to pi. Find the values of h of n for n equal to 11. Find h of z and plot the magnitude response. This is the problem we have to design it. So mathematically Hd of e power j omega is like this. So it is 1 from minus pi by 2 to pi by 2, otherwise it is 0, right? So Hd of e power j omega equal to 1 for minus pi by 2 is less than or equal to omega is less than or equal to pi by 2 and is 0 otherwise. So here n is given as 11. So Hd of n is equal to 1 by 2 pi integral minus pi to plus pi Hd of e power j omega to e power j omega and d omega, right? So it is 1 by 2 pi integral minus pi by 2 to plus pi by 2. Okay, pi by 2. Hd of e power j omega value is 1 from minus pi by 2 to plus pi by 2. So that's why it is minus pi by 2 to plus pi by 2. So e power j omega n into d omega. Okay, h d of power j omega n is 1, right? So we are applying the limits here. So 1 by 2 pi into e power j omega n by minus j, e power j omega n by j n with limits pi by 2 to minus pi by 2, or it is equal to 1 by 2 pi into e power j omega pi by 2. Omega is pi by 2 here. So pi by 20 n minus e power minus j pi by 20 n by j n. Okay. So it is equal to 1 by pi n sin pi n by 2. Okay. N equal to minus alpha to alpha. So h of n equal to h d of n at n equal to minus n minus 1 by 2 to n minus 1 by 2. Here n is 11. 11 minus 1 by 2 is minus 5. Plus here 11 minus 1, that is 10 by 2, that is plus 5, minus 5 to 5. So it is symmetric. That's why h of n equal to h of minus n. So h of 0 equal to, what is h of 0? H of n. So 0 by h of 0 equal to 100 remain. 0 by 0, 100 remain. Okay. By using L'Hospital rule, limit theta tends to 0, sin theta by theta equal to 0, and limit theta theta tends to 0, sin theta by theta is equal to 1. Okay. So using L'Hospital rule, limit theta tends to 0, sin theta by theta equal to n, limit theta tends to theta sin theta by theta equal to 1. Okay. So h of 0 equal to hd of 0 is equal to limit n tends to 0, sin pi by 2, sin n pi by 2 by pi n. Okay. So this is a hd of 0 equal to sin n is 0, sin 0 by 0. Okay. Limit n tends to 0 here. So limit n tends to 0. So it's 1 by 2. Okay. Similarly, h of 1 equal to sin pi by 2 by pi. That is 1 by pi. That is 0.318. H of equal sin pi by 2 by is 0, and h of equal sin 3 pi by 2 by 3 pi. So these are all the value. This is h of minus 1 value. This is h of minus 2 value. This is h of minus 3 value. And h of 4 equal to sin 4 pi by 2 by 4 pi, that is 0. That is h of minus 4 also. H of 5 equals sin 5 pi by 2 by 5 pi. It is equal to 0.065. That is h of minus 5. Okay. So h of z equal to h of 0 plus sigma n equal to 1 to n minus 1 by 2. H of n into z power n plus z power minus n. So by simply substituting these values, we will get h of z is this one. H of minus h dash of z is equal to h dash of z is nothing but z power. So here h dash of z is nothing but, see, this is the h dash of z is multiplied by z power minus of n minus 1 by this h of z. Okay, here n is 11, so z power minus 5 into this h of z. Z power minus 5 into h of z, right? See. So z power minus 5 into h of z, right? So z power minus 5 into this value. Okay. Simply, so h of 0 is filter coefficients. H of 0 equal to h of n is 0.636. So h of 1 is h of 9 is 0. H of 2 equal to h of 8 equal to minus 0.106. H of 3 equal to h of 7 equal to 0. H of 4 equal to h of 6 equal to 0.318, and h of 5 equal to h of 8 equal to 0.4. So magnitude response of h of e power j omega is equal to h of mod h of e power j omega, or mod h of omega equal to h of n minus 1 by 2 plus sigma n equal to 1 to n minus 1 by 2 h into n minus 1 by 2 minus n cos omega n. Okay. So or it is h of 5 plus 2h into h of 5 means 11 minus 1 by 2, that is h of 5 plus 2 into h of 11 5 5 minus n. Here n is 1. So 5 minus 4. H of 4 into cos omega into n is 1. So if n is 2, like that, we will write the expression. So these are the values for this values omega and h of e mod h of e power j omega will draw the spectrum. Okay, omega versus mod h of e power j omega. So this is about the design of ideal low pass filter. Okay. Like this, we can solve it. Okay, design this one. The next problem is design of ideal high pass filter. Okay, design an ideal high pass filter with frequency response which d of e power j omega is equal to 1 per pi by 4 is less than or equal to omega is less than 5. Find the values of h of n for n equal to 11. It is 0 for mod omega is less than or equal to 5 by 4. Find which object plot the magnitude response, right? Like earlier problem, hd of n equal to 1 by 2 pi into integral minus pi to pi hd of e power j omega e power minus j omega d over. But from pi by 4 to pi, this is 1. Otherwise, it is 0. So minus pi by 4 to minus pi, its value is 1. So 1 by 2 pi into minus pi by 4 to minus pi e power j omega into d omega. Okay, so it is calculated as 1 by pi n into sin pi n plus sin pi n by 4. So h of n equal to hd of n at n equal to minus of n minus 1 by 2 to n minus 1 by 2. That is here also n value is 11. So 11 minus 1 by 2, that is 5. So minus 5 to 5, it is also symmetric. So h of n equal to h of minus n, right? And h of 0 equal to, so it is 1 by 0. 1 by pi into 0 is 1 by 0. It tends to 0. Sin pi n plus sin pi n by n pi. So h of 0 equal to 1 by 2 pi into it's calculated by the from 80. So we'll get the 3 by 4. H of 1 equal h of minus 1 is this much. So like it will calculate the values of h of 5. So then h of z is this one, h of 0 plus sigma n equal 1 to n minus 1 by 2 h of n into z power n plus z power minus n. Okay. So it is 3 by 4 plus this one. So realizable filter at transfer function is h dash of z is z power minus of n minus 1 by 2, that is z power minus 5 into h of z. So in the same manner, so causal filter coefficients are h of 0 equal to h of n equal to this value, h of 1 equal to h of 9 equal to 0, h of 2 equal to h of 3 equal to, find this value, h of 3 equal to h of 7 equal to this one, h of 4 equal to h of 6 equal to this one, and h of 5 equal to 0.75. Okay, then h into the power j omega is equal to h of n minus 1 by 2 plus sigma n equal to 1 to n minus 1 by 2 into 2 into h of n minus 1 by 2 minus n into cos omega. So like that, we will simply substitute those values so that we will get the response like this. Okay, so like this, we'll do the problems ideal band pass filter frequency. So in the same manner, we will do the problem. And so ideal band reject filter with the frequency. So in the same manner, we will do this problem. You have to practice it on cap. Okay. So causality condition, not and non-causality conditions. All conditions are same. Okay. We have to simply substitute the values. That's all. And draw the response. Finally, we draw the response. Next, these are the Fourier series method. This is the Fourier series method. Next, the second method is the design of FIR filter using Windows method. Okay, using Windows method. Okay, so we'll discuss this Windows method, right? So second method is Windows method. So the procedure for doing the Windows method is the procedure for designing a FIR filter using Windows is choose the desired frequency response of the filter HD of e power j omega. That is the first point. Choose the desired frequency response of the filter HD of e power j omega. Okay. Next, take inverse Fourier transform of HD of e power j omega to obtain the desired impulse response, that is HD of n. Okay. Next, choose a window sequence omega of n and multiply by HD of n. That is the third point. Window sequence omega of n and it will be multiplied by HD of n. By omega of n, HD of n multiply omega of n with HD of n and convert the infinite duration impulse response to the finite duration, that is h of n is equal to HD of n into omega of n. The transfer function h of z of the filter is obtained by taking z transform h of n. Okay. Now window sequence for FIR filter design is like this. Name of the window sequence. So here we have different types of windows are there. So those are rectangular window, triangular window, Hamming window, Hamming window, Blockman window, and Kaiser windows. Okay, so for rectangular window, the window sequence will be WR of n is equal to 1 for minus of n by 2 is n minus 1 by 2 is less than or equal to n is less than or equal to n minus 1 by 2. It is 0 otherwise. Similarly, for triangular window, the window sequence is WT of n is equal to 1 minus 2n by n minus 1 for minus n by 2 is 2 plus n by 2. So it is 0 otherwise. Next, Hamming window, WH of n is equal to 0.54 plus 0.46 cos 2 by n by n minus 1 from minus of n minus 1 by 2 to plus n minus 1 by 2. It is 0 otherwise. Okay. Next, Hamming window, WHN of n is equal to 0.5 plus 0.5 into cos 2n pi by n minus 1 for from minus n minus 1 by 2 to plus n minus 1 by 2 and is 0 otherwise. So Blockman window, WP of n, its window sequence is 0.42 plus 0.5 cos 2n pi by n minus 1 plus 0.03 cos 4 pi n by n minus 1 from minus of n minus 1 by 2 to n minus 1 by 2, it is 0 otherwise. And the last one, Kaiser window, its window sequence is WK of n equal to I naught into alpha into square root of 1 minus 2n by n minus 1 whole square by I naught of alpha for minus of n minus 1 by 2 is less than n is less than n minus 1 by 2. So these are all window sequence for different types of windows. Okay. So now we'll see some problems. So design an ideal high pass filter with frequency response HD of e power j omega is equal to 1 from pi by 4 is less than or equal to omega is less than or equal to n and is 0 for W mod omega is less than or equal to pi by 4. Find the value of h of n for n equal to 11. Find h of z and plot the magnitude response having Hamming window. Okay, Hamming window. So what is step 1? So first of all, write the HD of n inverse Fourier transform. So HD of n equal to 1 by 2 pi integral minus pi to pi HD of e power j omega and d omega, right? Then HD of n is equal to 1 by 2 pi integral. It is varying from pi by 4 to pi. Okay. So from pi 2 minus pi by 4, its value is 1. So 1 by 2 pi into pi 2 minus pi by 4 e power 1 into e power j omega and d omega plus pi by 4 to pi e power j omega d omega. So it is 1 by 2 pi into pi 2 minus pi by 4 e power j omega and d omega plus 1 by 2 pi into pi by 4 to pi e power j omega and d omega. So HD of n equal to 1 by n pi into sin n pi minus sin n pi by 4. step 2 is panning window. So WHN of n is equal to having panning window. So for for a panning window, the sequence is window sequence is WHFN equal 0.5 plus 0.5 into cos 2n by n minus 1 from minus of n minus 1 by 2 to n minus 1 by 2, it is 0 otherwise. So it is equal to 0.5 plus 0.5 cos n by here n is 11 minus 1 10 by 2 is 5. So cos n pi by 5 from minus 5 is less than or equal to n is less than or equal to 5, it is 0 otherwise. So step 3 is h of n equal to hd of n into wh of n from minus 5 to 5. Okay, so hd of 0 is equal to that is n is 0 1 by 0 increment 1 tends to 0. Sorry, that is sin 0 minus sin. So that is 0.75. HD of 1 is HD of minus 1 is 0. Like this, we can calculate these values. So WH of n is of 0, 1, 2, 3, 4, 5 also calculated. So H of n equal to these two will be multiplied. HD of n equal to WHN of n. So we'll get the values of H of 0, H of 1, H of 2, H of 3, H of 4, and H of 5. Next, we'll see the transfer function of the filter given by H of z is equal to H of 0 plus sigma n equal to 1 to n minus 1 by 2, that is 5. H of n into z power minus n plus z power n. Okay, z power n. Right. So it is equal to this one. So we simply substituting the values of H of z. Next, step 5 is transfer function of realizable filter, that is H dash of z is z power minus of n minus 1 by 2 into H of z, that is z power minus 5 into H of z. So that will get H dash of z. So that is the realizable filter. Then causal filter positions are H of n equal to H of capital N minus 1 minus n. Okay. Okay. So H dash of z is equal to this one. H of n equal to H of n minus 1 minus n. So it is H of H of 0 equal to H of 11 minus 1, 10 minus 0. That is H of 10. Like that, we will calculate the values. So mod H into e power j omega is H of n minus 1 by 2 plus sigma n equal to 1 to n minus 1 by 2 2 H of n minus 1 by 2 minus n cos omega n. So simply substituting these values so that we will get the omega values and mod H of e power j omega, so that we will get the response for the panning window. So finally, we will substitute these values in this window sequence WHN of n. So that we will get WH of 0, WH of 1, WH of 2, WH of 3, WH of 4, WH of 5. Okay. So the quotients using panning window equates are H of n equal to HD of n cos omega H of n from minus 5 to 5. Like this, so we can calculate H of the base by simply multiplying this to get this value. Okay. So relative transfer function is this one. So the normalized ideal frequency response, that is Z frequency response for FIR filter design using Windows is for low pass filter, for high pass filter, and for band pass filter and band reject filter. The conditions are like this. So for low pass filter, HD of e power j omega is equal to e power minus j alpha omega per minus omega c is less than or equal to omega is less than or equal to omega c. And minus pi it is 0 from minus pi to minus omega c and is 0 from omega c to pi. That is for low pass filter. For high pass filter, hd of e power j omega equal to e power minus j alpha omega from minus pi to minus omega c. It is equal to e power minus j alpha omega from omega c to pi and is 0 from minus omega c to plus omega c. And for band pass filter, hd of e power j omega equal to e power minus j alpha omega from minus omega c to minus omega c1 and is e power minus j alpha omega from omega c1 to omega c2 and is 0 from minus pi to minus omega c2 and is 0 from minus omega c1 to omega c1 and is 0 from omega c2 to 0. So, and for band stop filter, hd of e power j omega is e power minus j alpha omega from minus pi to minus omega c2 and e power minus j alpha omega from minus omega c1 to omega c1 and e power minus j alpha omega from omega c2 to pi is 0 from minus omega c2 to minus omega c1 and is also 0 from omega c1 to omega c2. Okay, so that is the condition. Those are the conditions. Next problem is design a high pass filter using Hamming window with a cutoff frequency of 1.2 radians per second and n equal to 9. Okay. So the desired frequency response HD of e power j omega for high pass filter is already studied. So for high pass filter, this is e power minus j alpha omega from minus pi to minus omega c and this is e power minus j alpha omega from omega c to pi. Otherwise it is 0. So first of all we will write those expressions e power minus j alpha omega from minus pi to omega c and e power minus j alpha omega from omega c to pi and is 0 from minus omega c to plus omega. Here n is given as 9. So hd of n is equal to 1 by 2 pi integral minus pi to pi hd of e power j omega e power j omega and d omega and d omega. That is 1 by 2 pi integral minus pi to omega c. It is hd d power j omega d power plus 1 by 2 pi to omega c to pi. This one and otherwise it is 0. So minus pi to minus omega c it is e power minus j alpha omega and e power j omega and d omega plus 1 by 2 pi omega c to pi. It is also e power minus j alpha omega and e power j omega and d omega. Okay. So we simplify this one so that we will get hd of n equal to this expression 1 by pi into n minus alpha into minus sin omega sin n minus alpha plus sin n pi into n minus alpha. Okay, by using L hospital rule. So n equal to alpha. So hd of n equal limit n tends to infinity 1 by pi into n minus alpha minus sin omega sin n minus alpha plus sin pi into n minus alpha. So limit n tends to infinity n ten sin pi into n minus infinity by pi into n minus infinity minus limit n tends to infinity minus into n minus alpha by pi into n minus alpha. So hd of n equal 1 minus omega c by pi equal to alpha equal to n minus 1 by 2, that is 4. So like that all types of filters can calculate this band pass band reject. Okay. So this is about the windows methods. So different types of windows are there. Based on the windows sequence, we can solve those problems based on the windows sequence. Okay. Next one is frequency sampling. Frequency sampling method. sampling method. So design of FIR filter by frequency sampling method procedure for type 1. Choose the ideal frequency response HD of e power j omega. First, sample HD of e power j omega 10 points by taking omega equal to omega k equal to 2 pi k by n, where k is 0 to n minus 1. To generate the sequence HK of HK, h bar of k, that is equal to HD of e power j omega at omega equal to 2 pi k by n, or HD of omega. Okay. Next, compute the ensemble of h of n using the following equation. That is case 1. Case 1, if n is odd, then h of n equal to 1 by n by n at h bar of 0 plus 2 into sigma k equal to 1 to n minus 1. The real part of h bar of k into e power j 2 pi k n by n. N is even. Case 2, h of n equal to 1 by n at h bar of 0 plus 2 into sigma k equal to 0 to n minus 2 minus 1, real part of h bar of k into e power j 2 pi n k by n. So take Z transform of the impulse response of h of n. So to get the transfer function h of z, that is h of z equals sigma n equal to 0 to n minus 1 h of n into z power minus n. Okay, so that is h bar of k is equal to mod h of k. So mod h of k into e power j theta for linear phase filter theta equal minus alpha omega. So theta equal minus of n minus 1 by 2 into 2 pi k by n. So 2 gets cancelled. So it will become minus of n minus 1 by 1 into pi k, where k is varying from 0 to n minus 1. So the filter coefficient h of n can be obtained by finding inverse discrete Fourier transform of h of k. So h of n equal to 1 by n into sigma k equal to 0 to n minus 1 h k into e power plus j 2 pi k n by n, where n is varying from 0 to n minus 1. Okay. All these things we will discuss in next class. So with this, I'm concluding the today's class. Okay. So this chapter will continue in the next class. Frequency sampling method will continue in the next class. With this, I am concluding the base class. Thank you.